Hi, everyone. This is the last lecture in Unit 8, and the focus is on text processing using regular expressions. All right, so as we discussed in session 8.3, clinical data is complex and involves varying data structures. Most digital data being generated today is unstructured data. Text data, I should say. Natural language processing is a broad description of the techniques used to work with unstructured data that can assist computers in deriving meaning from these data sources. One important tool that NLP experts have at his or her disposal is regular expression. In this module, we'll discuss the use of regular expressions both generally and in the context of healthcare. So a regular expression is a way of finding, extracting, and sometimes replacing specific patterns in unstructured text data. Regular expressions are referred to as REs, regexes, and regexps. Relatively simple examples that everyone is familiar with is the use of simple wildcards in your search efforts. So if we want to query a text file and pull out all words that begin with a particular combination of letters, for example, we'll use wildcards to assist in identifying all possibilities. When used in a more sophisticated way, regular expressions can be used to find very specific patterns in text. Many of you have seen the increasing power of regular expressions in efforts to search increasingly massive data sets of text to identify websites of interest or to retrieve documents on your computer fitting certain criteria. Regular expressions involve the use of distinct notation that we will take time to review here in this PowerPoint. So while no standard language exists for regular expression notation, many programming languages use a fairly consistent notation. Perl-compatible regular expressions are one of the more common notation styles in use today. Remember that between languages, there will always be some variation. Taking time to reference your documentation to ensure you understand the particular regular expression notation being used by that programming language that you may have found working with is really important. So despite this, the concepts are similar and worth reviewing. So what are the capabilities of regular expression? Some of the more common functions you may be familiar with, in fact, you may already take them largely for granted in your daily life, include such things as searching for string patterns. So for example, you may have a body of unstructured health text and you want to search for all blood pressure readings from that given text. Given that blood pressure readings are often recorded as a fraction or ratio, you may find the development of a regular expression may be useful in your search. Complementing your search efforts, regular expressions can then extract search results that match your findings for further review and analysis. It's helpful in this context to think about the set of actions you take when you run a Google query. You begin by searching the internet for text matching a defined set of text values you have defined. The search then returns those values that match your description. Regular expressions can go even farther. In working with unstructured text, regular expressions can be used to replace text that has been identified with alternate text. You are familiar with these techniques through the use of find and replace regular expressions when you use word processors. Again, these expressions seem familiar because they are, and as a result, they may appear simple. Yet they are a very powerful tool in your efforts to derive value from health information. So what are the core elements of regular expressions? So there are three important elements to keep clear in your head when working with regular expressions. These three elements translate into the underlying coding of the regular expression and are noted in green. The first element is the pattern. This is what is referred to as the expression. This expression is a particular pattern of characters that you want to identify within the text of data. The original text or string of characters is the body of unstructured health data you want to search for the particular pattern. And finally, if you desire to replace a particular pattern of data found within the string with new data, then the replacement function along with replacement text is defined. So again, to keep in mind, there are three core elements to regular expressions: the pattern or expression you want to find, the string of characters you want to search, and potentially the text you want to substitute once the patterns are identified. As noted earlier, think of the find replace features within MS or other word processors, only much more robust. As you might expect then, understanding the core elements highlights some of the more familiar commands in working with regular expressions. So we'll discuss 4 more common commands in our exploration of regular expressions: the match command, the search command, the sub command, and the group command. Thinking for a moment about the elements of the regular expression we discussed, the pattern or expression, the string or text you want to search, and the replacement text can help in quickly understanding these commands. The match command matches a predefined pattern of text to a string and returns a result. The match command will only return the result if the pattern is identified at the beginning of the string, limiting the usefulness of this command. The search command finds the first occurrence of a pattern within a string and returns the result. This can be anywhere within that string. The sub command replaces all occurrences of the pattern or expression within the string with the replace text defined by the user or programmer. Think about your word processing program with its find replace command. Essentially, it's a natural language processing algorithm, only much more powerful in the context of mining health data for relevant data. The group command allows us to obtain a complete listing of the results of our search. And these 4 commands are really essential to the development of regular expressions. So we have a simple set of Python commands associated with the search and replace request. And so I'm going to pull this up on the screen here. And so first thing to note is that we have to import the regular expression library for use with our code, right? So that's that first command here, import regular expressions. Second, the string as we defined earlier in the text body that we want to search. In this case, we've kept with the Python tradition and are examining a portion of the Black Knight's rebuttal to King Arthur during their fierce battle for control of a key strategic bridge. So notice that we have named the entire string, it's just a flesh wound. And so, let's see, sorry, just getting my bearings here. So then the pattern we'll search for is flesh wound, a somewhat nonspecific medical diagnosis in this context, but still interesting. So we assign the pattern flesh wound, the name pattern for ease, okay? Okay. We then compile pattern using the compile command from the library and name it regexp to remind us that this is the regular expression in a compiled format. Okay, then the final step in programming our search and replace is to use the sub method to search the string defined above, defined here. It's just a flesh wound, and to replace the term flesh wound with severed limb. Note that that replace feature is done with using the .sub method applied against the regexp object. Notice the primary parameters of the sub, the parentheses, method are the replacement text and the string that you want to search. I'm just going to advance it one more time here so you can see. And the result of this code then is the phrase, it's just a severed limb, a much more diagnostically specific evaluation of the underlying injury. This initial example was designed just to provide you with an understanding of the basic use of search and replace commands. With this as background, we're going to continue to explore further the use of pattern-based techniques for more complex data searching and extraction. All right, so pattern detection is not limited to the literal text search features we just examined. Pattern-based parsing involves the use of more complex patterns for identifying words or phrases. Regular expressions include a number of special meta characters that can be used to represent generic patterns of text. In thinking about pattern-based parsing, it's helpful to think of it in terms of search engines and the use of wildcards to query for specific data elements. The term meta is defined as a concept which is an abstraction or representation of another concept. In this context, then, meta characters provide a more abstract definition of a particular character for the purpose of querying data. All right, so I'm just going to start at the top of this table and work my way down. So I'm hoping you can follow along here as I go. So there are a number of useful meta characters. A few of them are highlighted here, and they should be able to help you begin to see their use in the development of more abstract regular expressions. Again, note that the meta characters are used within the development of the regex pattern itself to introduce greater flexibility in matching the string or data set that is being queried. Okay, so the first one there, we have the pipe symbol, right? This is found above the backslash on your keyboard and is used to represent the logical or operator. Using the pipe symbol with at and home will allow the regular expression to match the string on either at or home. Then we have the period symbol. This is a single character wildcard equivalent. Using the period symbol within a regular expression lets you pull all values beginning with F and ending in O in the above example. So let me see where that, hold on one second. Okay. So FO is the example here. I kept thinking I had another example, but they're coming up. So in this example, it would be all characters between F and O, okay? And then the caret symbol sits at the front of a pattern and allows you to pull from the string any value starting with from. So similarly, the use of the $sign at the end of the regular expression allows you to pull strings ending with a particular value, okay? Brackets are next, and these are particularly useful in building conditional query capabilities into the regular expressions using the logical or operator. So the example of AB notes that either A or B will be returned if detected. The B, and then you see the bracket AEIU, another bracket in T pattern returns bet, but, or sorry, bat, bet, bit, and but. I do not have that in my notes correctly, so I had to look at the side, but the use of a dash between values will return all values within the designated range within the regular expression, okay? And then combining the brackets and the caret will allow you to invert the values you are looking to identify. And finally, the plus sign allows for the combination of smaller regular expressions into more complex patterns. So with these tools, and you might want to just as we go through the next ones, you can maybe pull up the PowerPoint slides that I have uploaded separately here to just maybe help you in deciphering these next expressions. Okay, so with these tools, we're going to, you could build fairly complex variable expressions that offer greater flexibility and improve search results. But we're going to look at a few examples in the next few slides here. So any thoughts as to what this might describe? Again, like I said, maybe you want to pull up from the PowerPoint slides that table that we just saw and kind of use that to decipher this. I'll give you a moment to take a look at it before moving on. And really amazingly enough, this pattern is designed to return a pretty simple output, okay? All right, I'm gonna let you pause it if you want, otherwise I'm gonna move right on, okay? So let's look at the elements here. So remember that brackets define a class for a single value. The capital A through Z is looking for a capital letter from A to Z. The smaller letter is looking for a single letter between A and Z. And finally, the 0 through 9 is looking for a single number, 0 through 9. This simple code is used to determine if a particular one-character value is alphanumeric. So let's go a little bit farther. So we've added a meta character here on the end. So what does that mean? Well, this particular code sequence will now match consecutive alphanumeric characters until they run out. They may run out because they hit a blank space or some other special character such as a pound sign or percentage sign that is not alphanumeric. As you might imagine, this type of regular expression can prove powerful as an element of a more sophisticated expression. But you can also appreciate how difficult it would be to continually type this expression for each word in a string. So the plus meta character is very helpful. So other special characters are available that we could use to simplify coding. So let's cover a few more here. So the /D matches any decimal digit. The /W replaces the code that we just walked through to match any alphanumeric. The /S matches any white space character. And as noted, these special characters are short forms of common classes noted earlier that simplify regular expression development. Armed with this information, let's see how well you do at detecting patterns in the regular expressions that follow. So how about this first one? I'll give you a minute to see if you can take this one apart. And again, I'll let you pause it. I'm going to go back because this will detect any simple web address. Next one. Take a minute to think about this one. Remember that the / special character is, what that is designed to do. So can you guess some familiar patterns here? This is for detection of any social security number. Okay, let's try one more here. So take a hard look at this one. There are 5 classes in this reference. The first is a capital alpha. The second, a small case alpha, A through H, then a number, a dash, and a second alphanumeric combination. Again, I'll let you pause it, or here is the answer. Chess, anyone? All right, another one. I'll give you a minute to examine this particular regular expression. When in doubt, start by breaking down the brackets. They represent the individual classes or characters being represented by expression. This one is really crazy. So we'll keep moving. But this detects any valid email address. Okay. So hold on one second. There we go. So if you guessed any valid email address, you were right? So as you might guess, these regular expressions follow common patterns, and as a result, we don't have to recreate the wheel and looking for a particular expression to assist us with more common unstructured data searches. Many of these are freely available at various online websites, such as www.regular-expressions.info. So this is interesting in general, but how about in medicine, right? Let's turn back to healthcare here. So as we discussed, a number of regular expressions are already in use in medicine. This particular chart identifies the regular expressions associated with vital signs. One of the challenges in working with medical data is that it is often unstructured, as I've mentioned several times now. Clinicians are known for their note-taking to record their assessments, treatment, and so forth. So accessing and deriving data such as vital signs requires the use of regular expressions to draw this information out as much as possible from unstructured data sets. As you look down the list, note that this particular author used a number of different designations of blood pressure in an attempt to pull out blood pressure readings, given that physicians all use different shorthand. Other vital signs are more simple. These expressions are also tied to better detection of more comprehensive blood pressure readings. To test the quality of these and other expressions, studies will be performed to look at the detection or signal accuracy of the particular expression in identifying the text of interest within the text string. It's also helpful to note that more advanced approaches to the use of regular expression will deploy them in steps in an effort to refine detection of the desired information. All right. Whew, we're at the end. So hopefully you have an appreciation for why we use regular expressions in medicine. Text and file manipulation are important in analyzing unstructured data, and it will remain for some time the real challenge of health informatics and helping organizations to derive value from clinical data. Regular expressions offer advanced capabilities that can assist in exploring larger text data sets that are more common in medicine. And finally, as we discussed, regular expressions are the foundation of a whole field of advanced health analytics called natural language processing, or NLP, which offers real promise in our efforts to achieve the triple aim objective of healthcare. Okay. And there's some references. I bet you guys are happy to be done with that one. All right. Have a great day.